Welcome to a course on complex analysis. In this lecture, we are going to see the polar coordinate system of a complex valued functions. All those things that are dealt in rectangular coordinates can be studied with the help of polar coordinates as well. As to give the justice to the statement that I stated, we are going to talk about the Cauchy Riemann equations in polar coordinates in this lecture. Let us explore them. In the previous lecture, we have seen the sufficient condition for differentiability, and we have seen an example that is f of z is e to the power z. So let us have a let us see one more example to justify that, and we'll move to the polar coordinate system. Okay. So the example that we are going to see is f of z is absolute of z squared. So if you look at what is your u, that is x squared plus y squared, and your v is going to be 0. Okay, the sufficient theorem statement tells us that it has to be defined in some epsilon neighborhood of whatsoever the point that we speak. Yes, of course it is there, right? And the first order derivatives with respect to x, so your ux is simply 2x and uy is 2y, and vx is 0 and vy is also 0. Okay, so the partial derivatives must exist and they have to be continuous at that point. Yes, all these things are there, so they exist, and all your ux, vx, uy and vy are continuous in, like, in all points. Actually they are continuous at all points. Okay, but they satisfy CR equation at only one point, and that point is the origin, right? So if this is so, then we shall write that point. Okay, f prime of 0. Here by 0, what I mean is that 0 plus iota times of 0. So this shall be written as ux evaluated at 0 0 plus iota times of vx evaluated at 0 0. So what is ux? That is 2 times of 0 plus iota times of, it is simply 0. So this is 0. So the derivative of the given function at the point 0 is 0 itself. Here by 0, what I mean is that a complex 0. Here 0 means a real 0. Okay. So whenever we write 0, you have to be very careful with what is the thing that we are denoting. Okay. Now let us move to the concept of polar coordinates. Okay. So yes. So here basically we assume that uh, z naught is non-zero. Assume z naught is non-zero. Then use the transformation x is r cos theta and y is r sin theta. So using the notations, we are going to do the things. Okay. Then our z equals x plus iota times of y may be written as what? R cosine theta plus iota times of r sine theta. You may take r outside, so this becomes cosine theta plus iota times of sine theta, and this may be written as r e to the power iota times of theta. Okay, with the z non-zero. Okay, and put w as f of z, and this may be written as u plus iota times of v. Okay, Here u and v are functions of x and y basically. Now they turn to be functions of what? R and theta. Okay, these things are happening. Now this f of z is a function of r and theta. If you wish to talk about the okay, here let us talk about the partial derivatives of u and v with respect to r and theta. So I wish to find del u upon del r. Okay, but u is a function of x and then that x is a function of r and theta. So what we will have is that del u upon del x multiplied with del x upon del r. Using chain rule we have this. Not only this, del u upon del y multiplied with del y upon del r. Okay, so we don't know what that u is. So we simply write this as ux, and from this we shall find the requirements. So those things I will do here. Yeah, we have x equals r cosine theta and y equals r sine theta. So del x upon del r is simply cosine theta, and del x upon del theta is minus r sine theta, and here del y upon del r is sine theta, and here del y upon del theta is r cosine theta. Okay, now we shall substitute these values into this. So del x upon del r is going to be cosine theta, and this is simply uy, and del y upon del r is sine theta. Okay, we have these things, and del u upon del theta, that is going to be del u upon del x multiplied with del x upon del theta plus del u upon del y multiplied with del y upon del theta. So this one we shall write it as ux, and this is minus r sine theta plus this is uy, and this is r cosine theta. So from which what we shall do is that we shall take r outside. So if you take r outside, then you have minus ux sine theta plus uy cosine theta, right? So similarly, we'll have to find del v upon del r and del v upon del theta. So del v upon del r may be written as del v upon del x multiplied with del x upon del r plus del v upon del y multiplied with del y upon del r. So this is vx multiplied with this is what? Del x upon del r was cosine theta, right? So this is cosine theta, and this is vy multiplied with sine theta, and del v upon del theta may be written as del v upon del x multiplied with del x upon del theta plus del v upon del y multiplied with del y upon del theta, and this is vx multiplied with minus r sine theta plus vy multiplied with r cosine theta. So from which we shall take v outside, then we have minus vx sine theta plus vy cosine theta. Now whatever we have done, so let us summarize these things and write here. This is for reference. Okay, this is so what we have done is that ur is sorry, so ur is ux cos theta plus uy sin theta, and u theta is, we have taken r outside, so minus ux sin theta plus uy cosine theta, and vr is what? Vx cosine theta plus vy sin theta, and your v theta is we have taken r outside, so minus Vx sine theta plus Vy cosine theta. Okay. Now we are going to impose an assumption that if the partial derivatives of the functions u and v with respect to x and y satisfy CR equations, it means what? That is ux is equal to vy and uy is equals minus vx, or vx is equal to minus uy. We may write either way. Okay. At some point z naught, then what we are going to have? So here we shall try to have everything in terms of uh, like we shall change these things. Okay. So you may write, let us have this quantity as it is, I suppose. Then actually we are going to substitute CR equations into this and see what we are going to see. Okay, let us try to convert everything in terms of the derivative of x. Okay, so if we have some derivative with respect to y, that shall be replaced with the derivative in x accordingly. Okay, so just a minute, let me write it in red color itself. So vy, yeah, good. So then ur becomes ux cosine theta plus uy may be written as minus vx sine theta, right? And then u theta may be written as r multiplied with minus ux sine theta, and uy may be written as minus vx cos theta. So from which we shall take minus also outside. So when we take minus outside, this becomes minus r ux sine theta plus vx cosine theta. Then vr may be written as vx, uh, yeah, so it is vx cosine theta plus vy may be written as ux, so ux sine theta, and v theta may be written as r multiplied with minus vx sine theta, and vy, yeah, vy is ux, right? So plus ux plus ux cosine theta. Okay, so these are the things that we have, and this may be written as r multiplied with ux cosine theta minus vx sine theta, right? So only these things we have. Now using these things, we'll have to compare and come to some conclusion. What is that? You just observe this v theta quantity and ur quantity. So from this, what you get is that your v theta is r times of ur. So that is very evident, right? So your v theta ux cosine theta minus vx sine theta, that is what is ur. So your v theta is r times of ur. And with the help of other two things, we are going to see. So you look at the value of this quantity and look at the value of this quantity. So vx cosine theta plus ux sine theta. So that is what we have inside. Since addition is also commutative, we can do those things. So your vr is what? Minus r times of, sorry, I am writing it wrong. So not your vr. So your u theta is minus r times of vr. So this is the Cauchy Riemann equations in polar coordinates. Okay, let me write that one. So this is CR equations in polar coordinates. So whatever we have done here can be stated as a theorem. Okay. So I am simply writing this as the theorem. You can just follow the theorem numbers consecutively. So this theorem tells you that let the function f of z is u of r theta plus iota times of v of r theta. Let this be defined throughout some epsilon neighborhood of a non-zero point z naught, which takes the form r naught exponential of iota times of theta naught, and suppose that the first supposition, the first order partial derivatives. So the first order partial derivatives of the functions u and v with respect to r and theta exist everywhere in the neighborhood. So this is the first supposition, and the next one is those partial derivatives are continuous at the point r naught theta naught and satisfy the polar form r u r equals v theta u theta equals minus r vr of the Cauchy Riemann equations at r theta, sorry, r naught comma theta naught. Then we shall write, so if these suppositions are there, then we shall write f prime evaluated at z naught exist its value being f prime evaluated at z naught multiplied with e to the power minus iota times of theta ur plus iota times of vr, where the right hand side is to be evaluated at the point r naught theta naught. Okay, we are not going to prove this theorem actually. So this may seem like the sufficient condition for the differentiability. Yes, of course it is in the polar version, right? We are not going to prove this. We have done the equivalent form, how to get the equivalent CR equations in polar coordinates from the rectangular coordinates. This may be done reverse as well, so I am not going to do this. If you people are interested, you can just try it out. Okay, so I am going to leave these things as they are, and now I am going to enter into problems involving polar coordinates. Okay, so the problems, let us start. So the first problem that we are going to consider is f of z is 1 upon z. So when you give the notation z is r e to the power iota times of theta, So this becomes 1 upon r e to the power minus iota times of theta. So when you express this, this is going to be cos theta minus iota times of sine theta. So with one condition, that is z is non-zero, right? So here your u of r comma theta is cosine theta upon r, and v of r comma theta is minus sine theta upon r. Okay, so now let us check whether it satisfies CR equation or not. So UR is what? Minus cosine theta upon r squared. Okay, and here VR is sine theta upon r squared. So here cosine theta and sine theta are to be treated as constant. So when you differentiate 1 upon r, you are going to get minus 1 upon r squared. So when you multiply that quantity with cosine theta, you are going to get minus cosine theta upon r squared. Here you have already the minus, so minus and minus gets cancelled and you have the remaining thing. And u theta is going to be minus sine theta upon r. Here v theta is simply minus cosine theta upon r. Right? So we are done. Now let us see what is RUR. Okay, R multiplied with minus cosine theta upon R squared. This becomes minus cosine theta upon R. So this is my V theta. So first condition is verified. Second one is uh, what? So it is minus RVR, right? So minus R multiplied with what is my VR? It is sine theta upon r squared. R and R gets cancelled. So minus sine theta upon r, which is nothing but my u theta. Okay. CR equations. Hence, CR equations are satisfied. Okay, good. So if you have to make use of the sufficient condition theorem, that is here the first of all the function has to be defined in some epsilon neighborhood of the point z0. So here the point may be any point except 0. So that we have said. Okay. If you consider any point except 0, look for some smallest possible neighborhood around it, and in that neighborhood the partial derivatives exist and they are continuous as well. Okay. Hence the derivative may be given a form. Okay. So hence your f prime of z may be written in the form that e to the power minus iota times of theta multiplied with ur plus iota times of vr. So to e to the power minus iota times of theta, what was your ur? That is minus cosine theta plus, sorry, upon r squared plus iota times of sine theta upon r squared. So from which I would like to take minus outside. So this becomes minus e to the power minus iota times of theta, and it is cosine theta minus iota times of sine theta upon r squared. Right? So it is minus e to the power minus iota times of theta multiplied with, this is again e to the power minus iota times of theta upon r squared. So this may be written as minus e to the power minus 2 times of iota times of theta upon r squared. So when you bring that quantity to the denominator, r squared e to the power 2i theta. So this may further be like, I don't know whether you people can see it. So this may be further written as minus 1 upon r e to the power iota times of theta whole squared. So this is nothing but minus 1 upon z squared. So if you directly differentiate this quantity, provided your z is non-zero, you are going to get minus 1 upon z squared, right? So that is what we have verified here. This next problem that we are going to see is, we are given a function f of z is cube root of r multiplied with e to the power iota theta upon 3, where r is a positive quantity and alpha theta lie between any interval of 2 pi. Okay, here if you expand these things, you are going to get cos theta upon 3 plus iota times of sine theta upon 3. Okay, therefore your u of r comma theta as cube root of 3 multiplied with cosine theta upon 3, and v of r comma theta is again cube root of r sine theta upon 3. So your u r is, remember you are going to differentiate with respect to r. So this may also be written as r to the power 1 upon 3, right? So let us write that way. That would be easier for us to calculate. So this becomes 1 upon 3 r to the power 1 upon 3 minus 1 becomes minus 2 upon 3, and cosine theta upon 3 is there as it is. So if you write this cosine theta upon 3 to the power r, so since it is given 1 upon 3, so let us write 1 upon 3 whole square. Okay, and similarly here your VR would be what? Sine theta upon 3 upon 3 r to the power 1 upon 3 whole square. So this is going to be similar kind of a thing. That is why I have skipped the steps. And u theta. So this becomes r to the power 1 upon 3 becomes, actually it stays as it is, and cosine would give you minus sine theta upon 3 multiplied with 1 upon 3. So this becomes minus r to the power 1 upon 3 sine theta upon 3 divided by 3, and your v theta would be r to the power 1 upon 3, and this is cosine theta upon 3 multiplied with 1 upon 3. So this becomes r to the power 1 upon 3 cosine theta upon 3 divided by 3. Now let us check the Cauchy Riemann equations. That is r u r. Okay, so what is r u r? So r multiplied with cosine theta upon 3 upon 3 times of r to the power 1 upon 3 to whole square, right? So if you look for it, you would get actually when you square it, okay, let me explain that too. So cosine theta upon 3, so this may be written as r2 to the power 3. Actually you have the power 1 here, so you bring that to down. So this is what you are getting, right? So cosine theta upon 3 divided by 3, uh, 2 upon 3 minus 1 becomes r to the power minus 1 upon 3. So in the denominator we have minus, so when you bring that to the numerator, that becomes r to the power 1 upon 3 cosine theta upon 3 divided by 3. So this is one way of doing it. Or you may have 1 upon 3 whole cube. You may have this. Okay, r to the power 1 may be written as 3 upon 3. Since we have 1 upon 3 here, we wish to write it in that form. You can give 1 upon 2 whole square. That form may also be given. But based on the problem, we are giving the forms. Okay. So I have not done this way. I have done it in the other way. For the rest, for the next thing, I will do that way. Okay, this is my v theta. Similarly, next minus r vr. So minus r, what is my vr? So it is sine theta upon 3 divided by 3 r to the power 1 upon 3 whole square. So here I am going to do that approach, r to the power 1 upon 3 whole cube. Next sine theta upon 3 divided by 3 times of r to the power 1 upon 3 whole square. So the square term and cube gets cancelled, and I am left with minus r to the power 1 upon 3 sine theta upon 3 upon 3. So this is my u theta. So hence CR equations are verified. Okay, after verifying CR equations, let me write the derivative as e to the power minus iota times of theta, and I'll have to substitute my UR term. So my UR term is what? R to the power 1 upon 3. Sorry, UR I'll have to write, right? So my UR is cosine theta upon 3, cosine theta upon 3 divided by 3 r to the power 1 upon 3 whole square plus iota times of, then we'll have to write the VR. So VR is, instead of cosine we are going to have sine, that's it. So iota times of sine theta upon 3 divided by 3 multiplied with r to the power 1 upon 3 whole square. Okay, if you take these things outside, you are going to have e to the power minus iota times of theta upon 3 r to the power 1 upon 3 whole squared, and this would be cosine theta upon 3 plus I times of sine theta upon 3, and this may be written as minus e to the power minus iota times of theta 3 upon r to the power 1 upon 3 whole squared, and this becomes e to the power iota theta upon 3. Okay, so this is what we have. So when you combine these two things, you are going to have e to the power iota 2 theta upon 3 r to the power 1 upon 3 whole squared. Okay, so when you bring that to the denominator, like uh, sorry, I think I have done a mistake here. We have minus, so minus iota, so you can bring that to the denominator. So 1 upon 3 r to the power 1 upon 3 whole squared, and e to the power when you bring the minus quantity to the denominator, it becomes positive. So this quantity is there. So this may be written as 1 upon 3 r to the power 1 upon 3. So that one we write it as cube root of r e to the power iota theta upon 3 whole squared. So this was the given quantity, right? So 1 upon 3 f of z whole squared. So this is that. Okay. Thus what we get is that f prime of z is 1 upon 3 f of z whole squared. So this is valid. So from this you can very well observe that we have found the derivative of z to the power 1 upon 3, and that turns to be 1 upon 3 z to the power 1 upon 3 whole square. Okay, we have seen. Yes. So with which we conclude the this lecture. In the upcoming lecture, we are going to talk about the analytic functions, and followed by we will talk about the harmonic functions. Thank you.